So, so let's jump in. So we just finished running a little car down the track and shrinking the width of that cardboard piece to show how we went from average velocity to instantaneous velocity. I want to, for a minute, kind of talk about a constant velocity. And I want to develop kind of a coherent model and statement of things that are not speeding up and not slowing down. So we've already looked briefly at our car going down the ramp, which was something increasing in its velocity, and we saw what that graph looked like. You knew what it all looked like. Good job, you got it. And so let's take a look. What would it look like if? What would it look like if I had a constant velocity on a position versus time graph? Okay, it's a linear graph. Okay, so there it is, a position versus time, and I have a beautiful line on my graph. And there is a function, a mathematical function for that, right? It'd be a y equals mx plus b, good. But instead of using a y, instead of using an x here, I am going to plug in the stuff off my variables, off my axes. I'm going to use x and t. So I'm going to say x as a function of time is equal to, the slope is, in this case, it's the velocity. Now, this velocity is an average velocity. It's a constant velocity because the slope is the same everywhere. Plus xi. Okay. So this formula should actually be familiar. This looks just like the formula read in our chapter for position with an acceleration set to 0.
Uniform motion, that's what it's called.
Uniform motion, correct. Uniform being the same. I apologize. Let me move this track out of your way. All right, so here we are. We're doing uniform motion. And we have our equation of motion. Let me write down what I just said a moment ago. What I just said a moment ago was that this is, let me not write that. This equation here okay, so is the equation off to the right in red somewhat familiar? It's one of our equations of motions. It's x final equals 1/2 at squared plus initial velocity times time plus x initial. Yes? You've seen it before, I hope? It's a position equation, absolutely. Now, if a is 0, this whole term goes away, and it reduces to this. So this is not, I want to emphasize to you, this equation in blue is not a new equation. It is the same position equation we use in the summer homework. It is the same position equation you would have read in this chapter or used for any other situation, but we're just setting a equal to 0 because we set the motion as constant, uniform. There's no acceleration going on. Okay? However, that blue equation, I didn't derive from the red equation. The blue equation I got from my perfectly straight line of position and time. Okay, my 9th graders did this lab the first day of school. They took little tiny cars, electric cars, that go at a constant velocity, and they put pieces of masking tape on the floor every meter, and they timed it with lap, lap, lap on the stopwatch. And sure enough, the graph of the motion of those cars looked just like this beautiful straight line. Good? They linearized it with the best fit line in a calculator. Got a linear regression, a linear fit. Okay, and they go, boom. That slope of that line is the velocity of my car. Okay? So this is pretty simple stuff. What I want to do is I want to look at other ways to kind of represent this motion, other ways to show what we know about how this is moving. So what would it look like if you drew a graph of velocity versus time, where velocity is in meters per second?
It's just a straight line.
It's a straight line. Okay. Why is it a straight line horizontal? Because you're graphing a constant. Okay. So since we're graphing a constant, we just go like that, and boom, it has a slope of 0, correct? That line has a slope of 0. And the y-intercept, what's the y-intercept?
The initial.
Yeah. It's my average velocity from up above, right? So whatever my slope was here, right? That is now my y-intercept down here. Today is the 7th. Yes, all day. Okay, so now I have another graph. And if I wanted to look at my bottom graph and I wanted to figure out, let me ask the question differently. So how about I look at my top graph? If I look at my top graph up here and I want to figure out how far I moved up here compared to where I started, what would you look for on the graph? So again, this green dot is where you ended up. This other green dot's where you started. How would you figure out your displacement, your change in position from beginning to end?
Area below the line.
It would not be the area below the line for this graph. No.
You're gonna cut it out like without the initial starting position.
Okay. What are you gonna say, Mason?
I was gonna say just use the top one.
Yes. Yes. Is that what you meant also by cut it out? Hopper? Oh, fine.
No, I was going to ask you to repeat the question.
The question was, how do you find your displacement off this graph? And the answer is you take the y value up here, which is your x final, you subtract away the x initial, and you find this distance on the y-axis. That is your displacement. It goes from where you started to where you ended. Because the y-axis is your position, yes? So therefore, the initial position is at the bottom, the final position is at the top, okay? And so I'm going to write xi at the bottom. I'm going to write xf at the top. The definition of displacement is just this. That's the definition of displacement. We good so far? Okay. How would you find displacement? Don't call it the answer, please. On the bottom graph. How would you find displacement on the bottom graph? Nathan, you got an idea?
Forming.
Okay. Kaya?
Integral.
Take the integral. Now.
That's what I was going to say.
No. Now, she's correct, but you know how to do this. You just don't know that word yet. So tell me, how would you do this?
I would have multiplied. I would have just taken whatever the y value is.
Right.
Because it's constant.
Yeah.
And multiplied how long it goes.
Yeah. And that is called an integral in calculus.
Get out of here with your fancy words.
Now, please note that these two terms are in my blue equation above, aren't they? If I take the xi right here and subtract it from both sides, I end up with xf minus xi. Okay? And so this term right here, see v times t? V times t is displacement. And what Nathan just told me to do is, hey, take that v that you have right there, multiply it times the time right here, and you're going to find the area underneath my, I'm going to use the word curve. I know it's a straight line. I'm using the word curve in the most general shape of a line. It wouldn't have to be a straight line. It could be a curve, and the answer would still be find the area underneath it. Now, of course it is. It's base times height. You don't need, because it is a rectangle, not a square. And so you do not need to use calculus for this because I have a perfectly straight line for my red velocity that's constant. However, if it was some crazy looking thing that looked instead more like this, it was v and t, and it looked more like that, that'd be harder to take the area underneath. Okay? And to do this kind of shape, you would actually need calculus. Maybe that's some kind of sine or cosine that is damping, that is getting smaller and smaller in amplitude as it goes. Motions that do that, if you let any kind of thing swing back and forth for a while, it swings less and less over time. Or if you've ever been to a restaurant and seen the door between the kitchen and the area where the people are, it swings and it just swings less and less over time until it critically damps out. Okay, so this is a damped sinusoidal function, and you could find the area underneath the damped sinusoidal function. You could actually shade this in And using calculus, you can calculate exactly how much area is there, and that would be the change in your position or your displacement. Okay? Yes. And we will not do that probably until the spring semester here. Why? Because I want to wait for you to get to all your integral stuff in calculus. I don't want to teach you all the integral stuff. There's no need to do that because I can teach you every concept I need doing something much simpler over on the left over here. Okay? I can do this, and with this kind of setup over here, I can test all the concepts of physics that I need without doing the complicated math step of finding the area. Yes?
What is a word? Like
Integral. What an integral means, really, just to put it in extremely brief language here for us. What the integral is going to tell you, not blue. Hang on, let me find another color.
what's the area of the line?
No, it's specifically, it's reverse engineering what we did in the derivative. So here's what it does, is it cuts this area up into an infinite number of slices. Every slice has a width of, can you guess? dt. And it adds up the area of each little slice individually. Because if the slices are infinitely small, then let me go over here. If this little slice right here is infinitely small, it doesn't have a changing y value as a single y value because it's like a dot. And so what you have is you have a infinitely thin rectangle that has a single height at the top, okay? And it has a very narrow width. And you add up all these different rectangles at these different heights, each one of its own area, and you find the total area underneath. Okay? Now, think about the word integrity. If someone has integrity, their words and actions add up. Have you ever heard that before? That your actions add up to your words. The same is meant here with the word integral. What you do is you take the area of each one of the rectangles and you add it up to be the sum of the whole. Okay, so the word is integral. Can I help you, Robert?
Sure.
You can. Rest on. Okay. He's more than entitled to it. I just think it was funny that I asked Robert for help and not the Mr. Runowitz.
Sorry for disturbing your class. I didn't have a chance this morning,
I understand. Not a problem at all, sir.
which I'm sure you figured out if your lights are on.
I fully understood. So let's carry on. So we've looked at 3 different representations here. We looked at position versus time, a velocity versus time, a very simple equation, and we've kind of played with a simple equation. Okay, and that is the issue. This is the story right here of constant motion. Okay, so let me ask you 1 or 2 follow-up questions for you, and then we will move on to much more interesting accelerated motion and other things that are not so boring. Okay, and we'll be done with this. I do want to make sure that whenever I refer to things that move at a constant velocity for the rest of the year, that you actually know that this is the model right here that we're going to be using, where A is 0, and all the equations of motion simplify down where A is 0, and that these are the graphs associated with it, and that the area of the graph is the displacement. Those kind of things that will just be native to you, okay, as we go through. And I will just mention 1 or 2 other quick details here that are, I'm going to say, really obvious. Did not mean to go that far down. Right here, how would you graph acceleration versus time for this? Someone just call it out, please. It's 0 on the x-axis. Boom, right there. Okay. Why? Because it's 0. Because you're graphing the slope of the line above. What's the slope of my v versus t graph? 0. Okay, so this is so trivial. I almost didn't mention it, but let's mention it. Okay, now let's go on and ask a couple of questions, okay? Traditional questions that are asked like this are sometimes called collision problems. So let's say you have a train on the tracks. Let's say you have a train on the tracks, okay, and here's your train, and it's going this way. It's going this way at V1. The nose, I don't know. Aerodynamic. Hey, sorry. So sometimes you draw something and then afterwards you're like, that was not really beautiful.
It has a shield.
Yes, it does. It is a battle train. Okay, and so, and here's a bigger train. and this one has its own speed v2, and in between them is a distance delta x. Okay, and so if you were graphing their position and their time like so, and let's give some of these values numbers here. Okay, so we'll say that V1 is 30 meters per second, and we'll say that V2 is 60 meters per second.
It's a train, dude.
For two trains, obviously.
He's making fun of my-
I can tell. I'm defending you, man. Okay, and in between here is 400,000 meters, 400 kilometers. Okay. When will the trains actually hit? When will the trains hit, and where will the trains hit? So the trains each have a speed. Their speeds are constant, coming right at each other.
The system of equations and line cross.
Okay, why don't you please draw it and figure out what that might be for me?
Alright, I will, Johnson. Watch and learn. The velocity is 30 and it starts. Wait, what is the 400,000?
It's the distance in between them when they start. That's
Okay,
right.
so this one starts at 0. That's 30.
So how long do we have to the collision, and where will the collision occur?
Starts at
The other two look so bored. It's so sad.
Wait, is there one, like, is this like obvious and I'm just like,
No,
oh, okay.
they're just like, well, good. If Popper's gonna do it, I'm not gonna do it. Johnson, do you have an answer?
Sort of.
Graph it. Okay. So version 1 is graph this.
That's a question.
Yeah.
So for this specific question,
Yeah.
we just add up the speed and we're use the distance to divide us the speed. So we find the specific time where the hits,
Yes.
and then we just
Work backward, or plug it into one of the
Yeah.
speeds and find the position.
yeah.
Yes, you could do that also. Yeah, that's using a different strategy to solve the problem called relative velocities. Yeah. Mhm. Okay, then I want to ask the question: what if train 1 starts moving 1 hour after train 2?
No, it's just,
Is there like those algebra 2 problems?
Yeah, this is definitely an algebra 2
Where
kind
we
of
have to,
problem.
like, make a little chart, like, and then,
You don't have to make a chart. I would say if you are clever, you can do this without making charts and such. I hope you're clever too, kiddo.
4,444 seconds.
Really? How'd you find that?
I don't know.
No, that's not right.
Let me check.
I didn't say it's wrong. I just said how'd you find it? That's all.
Wow. I should write.
How'd you do it so fast?
I approve it. How'd you do so fast? You just. How did I do that? Because it's 30 plus 60. That's the total speed they're going for. If they're going this way, and they're going the same distance, they're going at 90 meters per second total.
So here's what we're gonna let's talk through it Johnson's way because it's useful to understand Johnson's strategy. First, I want to graph the first problem. The first problem I would graph like this, and then I would graph like, ooh, that was not what I meant to do. Then I would graph markup line. That's what I wanted, and then I would graph like this. Okay, and I would intersect them. And I would give one of them a slope of 30 meters per second, and I would give the other one a slope of negative 60 meters per second. Okay, and I would find the intersection point. Let me ask, how would the graph change if the first train left, the 30 meter per second train left, an hour later.
It's part of the distance they went, so I know it's minus, right? I know it do the same thing.
Yeah, you would just scooch this line over. You would take this line and you would just drag it over until the intercept on the x-axis was 1 hour. So the time right here was 1 hour.
Which is train one.
I told you the 30 meters per second was. If the other one was, it would just start at 1 hour, right in the middle of space, and go down, okay? Which would be okay also, just look a little more awkward. So you would just change the way you graph it like that. So are we good handling that little issue there? Okay, so, okay, what did Johnson do? Johnson said, and his strategy is also valid, he said it's much easier to deal with one equation and one unknown than two equations and two unknown. So let me set one of the velocities equal to 0. And what he's going to do is say, if I'm actually driving this train right here, I'm going to pretend I'm at rest. I'm going to say, how fast is the other train coming at me? And so he would take the 60 meters per second it's traveling compared to the ground. He would add in his own 30. And he would say, relative to me, the train's coming at me at 90 meters per second. And I'm sitting still. Then you only have one distance, 400,000 meters. You have one velocity, 90 meters per second. And you have one time of impact, okay, when you actually come together. And it simplifies the situation. And what he did in physics, we call that changing your reference frame. Okay, it's changing your perspective. It's saying now instead of standing on the ground, because these 30 and 60, those are the speeds that you get standing on the ground. But if you don't want to be standing on the ground, you can shift your perspective and you can be standing on one of the trains. You simply have to subtract 30 or go 30 meters per second to the left for both trains. Okay, so for the first train, and I'm writing all over things here. So for the first train, I'll draw as a box now, just to keep it simpler. So this one's 30 meters per second to the right, and this one we said was 60 meters per second to the left, which could also be seen as a negative 60. Right? So if you do 30 meters per second minus 30 meters per second, obviously you get 0. Over here for the other one, you get minus 60 meters per second. The minus is because it's going left. Minus 30 more, okay, and you get minus 90. He shifted reference frames because it was easier to solve the problem from the point of view of driving on one of the trains or from the frame of reference of driving on one of the trains. We will solve other problems this year where we shift reference frames because the problem is easier in a different reference frame. Okay? It's kind of like in calculus sometimes, you'll shift a coordinate system. You'll shift maybe from Cartesian to polar coordinates. It's easier to solve a problem. Jonathan's like, that's never easier. Sometimes you'll shift coordinate systems because it's easier to solve in a different perspective, a different frame of reference, a different coordinate system. Okay? So that's called, sometimes it's also called a Galilean transformation because Galileo came up with the idea that literally, I think the quote is, all smooth motion is relative. That's the way he said it. Newton hadn't come along yet and said an object in motion stays in motion. And so this predates Newton's work. All smooth motion is relative. Galileo came up with that law, and that law, I would say, is fundamental in all of Western science and has never been seen to be violated yet. All smooth motion is relative. All of Einstein's relativity, all of Newton's work is all based on that idea. Okay? That you're allowed to shift reference frames, and there's no preferred reference frame. As you read the book into the next chapter we're going to be in, you'll start to see things about inertial reference frames. Inertial reference frames are frames that are either at rest or at motion in constant speed. Okay, and so those are something like, you've heard an object at rest remains at rest, an object of motion remains in motion. So if you're at rest or at constant speed in a straight line, you're in a reference frame where Newton's laws are going to work. And that's another area we're going to use the phrase reference frame. Okay, so all that was good. All right, we're now kind of done with constant velocity or uniform motion. Let's kind of leave it behind and let's jump into more interesting things like acceleration or free fall. Do you need me to show and or prove, because we're running low on time, we have about 20 minutes, that on a hill like this, if there is no friction, when you are sliding down the hill, the A is g sine theta. Are we comfortable with that? Do you need to prove that, or are we comfortable? Mg would be the force, not the acceleration. F equals ma.
Because you only use G as acceleration.
So the force of gravity or the weight is mg. But if I'm only asking about the acceleration, then you would divide both sides by m. On the left, you would get the acceleration. On the right, you would get g. You with me?
Just cut that down.
Okay. And a lot of things in class, we meet so early in the morning sometimes here for some of us that your brain's not fully turned on, and you're just like, yeah, let me copy that down. Let me just look at it later and get it later. Okay, and that is good to do. So all we're saying here is that if you did want to find the weight, of course, in this equation right here, you could multiply, Nathan, both sides by m. And you would have ma, which is the force, is equal to mg sine theta.
Why is F over M?
Yes, because F is ma.
What is this section called? The first one was constant, but it's on the weights.
Constant acceleration. Okay, so now we're in constant acceleration. I actually just bounced to the last section of the chapter, but I'm asking, do I need to show this? Do you need to see someone work out again?
No, it's good.
You want to?
Oh, we can do it.
Okay, so I'll ask you to come in for tutoring, or you can also watch the first summer session video we did in class, the first day of school, and we did it there. Okay, and I also did this on the summer homework for homework set 3. Okay, video 3, I did this. Okay, so you can see this in a number of places where we do that triangle, and we show that the triangle of the hill is the same as some triangle here. Okay, where this is my g sine theta side, and this is g, and this would be g cosine theta. Okay, so this angle is the same angle as the hill. So I'm not going to do the whole problem again. Yes?
I think you uploaded the wrong video
For 5.
4.
5.
And use one of those. I think it's 4.
4 is wrong too?
Yeah.
No.
4 is only like 2 minutes.
Okay, that was 5 part 2.
Oh, yeah.
And I uploaded the wrong video, or I uploaded another video on top of that one. I apologize. And so I will fix that as soon as class is over. Okay? Because I found the correct video. I just have not uploaded the correct video. I will do that. Yeah, that was just recording another video for another class. And dragged it up by accident. Okay.
Is that for the freshmen? One thing? Software?
Yeah. They were doing homework. And I just gave them a 2-minute help on their homework because a lot of them didn't know how to use the software. They do. They need a lot of help. They're good kids, though. They work hard. Okay. So let's jump into the idea of the acceleration. I'm not going to run through the calculus right here. I'm not going to run through the derivatives, and I'm not going to run through the integrals. You know derivatives quite well. We discussed at the beginning of class for 20 minutes with the car and the track and on paper and all that, the idea of instantaneous velocity. So I think we've done that pretty well. I'm pretty confident that you have a grasp on that concept. So I just want to leap right into kind of working some kinematic problems with acceleration being constant. And whenever I use the phrase derivative, what I'm always talking about is the slope of a function. When I use the phrase integral, I'm always going to be talking about, can you guess? The area underneath the function, okay? So derivative is synonymous with slope. And as of today, integral is synonymous with area, okay, when you have to grab something. So we even looked at together the first day of school in the summer homework, our basic equations of motion. Right, and so we saw some equations of motion where this is our definition of acceleration. Okay, and when a is constant, okay, when a is constant, then you come up with an equation for velocity by doing this step here. And the first day of school, we did the opposite order. We went from the statement below. We took the derivative and got up to the statement above. Okay, that's what we did the first day of school. Okay, Sometimes the v on the left is written as v final. Sometimes the v on the left is written as v as a function of time. It just kind of depends on how you're working with it and writing it. Okay, so these two are the exact same equation. It just depends on how you want to express the one on the left.
I don't get it, like why the
When you have a graph like this of say x and t, let me not do that graph. Sorry, just kidding. Here we go. So let me do this graph. Let me do a graph of v and t. And I have a line like this. So this is vi. And whenever I stop at the end of the problem, this velocity right here is often called vf.
yeah, but why is it?
Because you can also find the velocity at any other point you want, there or there or there, using the exact same equation, because this is actually an equation for velocity as a function of time. If you plug in a different t, you get a different v. So if I plug in a t right here, then I didn't really want to do that in the marker. If I plug in a t right here, I can go up and go over and get that v. If I plug in a t right here, I can go up and go over and get that v. So there's a one-to-one correspondence in the function between the times and the velocities. So we often express it as v as a function of t. Yes.
So for this section, what's the name? This acceleration or still constant?
In the book, we are in section 2.4 called motion with constant acceleration. Okay. A lot of people start out in this section right here. We just finished chapter 2, by the way. Chapter 2 will be done in 5 minutes. As far as covering the content of it, we'll have some problems to work on it now. A lot of people at this point in the course feel like most problem working is doing equation hunting. That is, okay, you give me the equation, I can work the problem. And that's a huge mistake, because when you think of it as equation hunting, then you're thinking of it as a math problem, not a physics problem. Okay, the math is a final step you do at the end. Okay, let me just do 400,000 divided by 90, got an answer. The time. That was the train problem, right? And so it's a final step you do at the end of the calculator after you've already set up and understood the problem. Okay, and so it's not about let me choose the right equation. It's not. All right, I want to push and emphasize that. And so we will look at problems and kind of study the whole approach. And so if we take the integral of this, we get the equation that we saw up at the top, which I'm just going to jot down. So all these equations are in the book. And when we saw them the first day of school, once again, we played with them or introduced them by doing derivatives. So if you take a derivative of this one, you get to that one. If you take a derivative of this one, you get to the one above. And so we did derivatives the first day of school. I'm writing them in the opposite order now, because they're always found in the opposite order. And if later in the year we work problems that do not have a constant a, never fear. You can just go through the very simple process of doing our antiderivative once and finding the area or the integral, and boom, you have a velocity function. But again, you have a position function. And the functions will look different when a is actually a function of time, okay? Because if a was like 3t squared, okay, then it would have a different function, okay? All right, so these are constant A's. The best example of constant A is the example of free fall. Free fall means that gravity is the only force acting on it, so we only have to deal with 9.8, or if you're on a slope, 9.8 times sine theta. There's no other forces, there's no frictions, there's nothing slowing anything down, all right? And so then we can jump in and start to work some problems. Let's just start some really, really simple problems. So I will just do a really simple problem here. I have a pen in my hand. This pen is 1 meter off the ground. If I drop this pen and it reaches the ground and it fell through 1 meter, please tell me how fast it was going right before it struck the ground. For this, you will need a calculator. A phone will do. And you will need the equations that I just put on the board. Okay. So I just gave you a problem. A pen falls through 1 meter. It strikes the ground. Please tell me the velocity of the pen right when it strikes the ground. I don't know. I don't think I gave it to you. So if you have not yet begun, if you're just sitting and staring going, where do I even start with that problem? You always start with the given, okay? When I work problems and I don't know what I'm doing, I literally go through this mental process that someone showed me a long time ago. And the first thing you do is you write down the given information in the problem because I don't know anything else. So I'm going to say my delta x is equal to 1 meter. That was my displacement that was given. I'm also going to write down the other piece of information, which was that I know the acceleration due to gravity is going to be g. I also know one other thing. I dropped the pen. I didn't throw the pen down. So my initial velocity is 0. So let me just state explicitly, those last two numbers were not said out loud. But they were, I dropped the pen in front of you. You could watch me. I didn't throw it down. And so its initial velocity was 0. You have to read into the problem a little bit. Acceleration is g. This is a free fall problem. That's the only acceleration we ever have. You're staring in confusion a little bit.
I just think that we sleep time.
You don't. Yeah, you don't. Or you do, and you have to go find it. Okay? In which case you can do that.
Oh, okay. You put all those three numbers into the final one, the binary equation, and then calculate p, and then you put p back to.
You could do a system of equations here. Yes. Or we're going to remember one more equation. So let me. Yeah. Okay. So. Let's just, and we actually should probably show that one at some point, but I'm not gonna do it today in the interest of time. I have 10 minutes left. So let me say two things I did. One, I wrote down the numbers that I knew. Two, I put them with variables. It's extremely important that you just don't write down numbers, but you actually put the variables with it, because as Mason just did, oh, look at the variables I have. Now I can use that equation. Picking out an equation is not random luck. I tell you what, some people, especially in first year physics, they look at a long equation sheet, and they're just like, eeny, meeny, miny, moe. It's like pin the tail on the donkey. You know, and they're hoping to get lucky. And because they're just equation hunting, they don't know what they're doing. Right? And man, they just see an F in an equation, they're like, I'm gonna put a force in there. That F is for focal length of a lens. It was not about forces. I was an F, man. You just put it in there. Okay, I'm gonna make that work. And so, but that's not the kind of strategy I want you to use. I want you to be able to put the variables down that it goes with. Then the second thing I do is I lock in on what I'm trying to find, which in this case is my unknown. And my unknown I asked you for was the final velocity. Okay, I might have to find time as an intermediary step. Okay, if I do, so be it. And then I jot down, hey, what equation do I want to use? There is an equation I did not put up above, and it is this equation. I often refer to it as Galileo's equation. I like that reference. I was chatting with some Europeans once, and they said that they called it, when they were in school in Europe, they called it Galileo's equation because Galileo had a very, very hard time measuring an elapsed time because there were no stopwatches. Okay, they couldn't even count a second very accurately. I don't even know when a second became defined. Okay, but it was after Galileo that a second became, I'm going to say, very carefully defined. And so this equation is not magic. You arrive at it by manipulating the equations above. Okay, and we will show that some other time in class, or I'll just record a little video and put it up online, and you can watch it if you want to. Okay, so let's make some substitutions.
How do you decide how long?
Yes.
Yes, very good.
We had Dessa.
Dessa, what was Dessa?
Maybe it was Dessa. Remember Dessa? I was like,
It's not Dessa.
it was.
Hello.
I don't care about that.
I don't remember the D, but I remember the E was equation, the S was substitute, and then the A was the
It's
answer.
not working for us in all the see it.
I think in this case, well,
Yeah, I just lost something. Hang on one second. I'll try and get it back.
it's imagine how far.
What is it even called, that thing? I can't remember anymore.
There's a mirror for the movie. That's cute.
Okay, Johnson, 1 second is the time that elapses during 9,192,631,771 cycles of the radiation produced by the transition between two levels of the cesium-133 atom.
What?
Yes, per second.
That's how we decided what the second one?
Yeah, they wanted something very consistent, so they took the vibration of the nucleus of a cesium atom.
I mean, they decided that later. That's not what they originally shipped.
Correct.
Really?
No, you're correct. That's not what they originally chose. Right.
They just said,
I mean, come on. Atoms weren't even proven to exist till Einstein came around. No one knew about nucleus till Rutherford. No one could measure the vibration of the nucleus until, probably post World War II.
they just like chose, oh, that was kind of
Yeah.
fast.
Are we back? We're back. Okay. So we had a little driver crash there. Sorry about that. So there's our substitute step in that we solve. This is pretty straightforward. What is 2 times 9.8?
19.
It is 19.6. In this class, if you want to use 10 for G, you are always allowed to use 10 for G. Unless we're in a lab situation, you need to use 9.8 in a lab situation to get the actual right answer. On any math problem ever, or on the AP test, at any point in time you feel like it, you may use 10 for gravity, for simplicity of numbers. Once again, it is not a math test, it's a physics test. Okay? And by approximating G to be 10, you don't change the physics in the problem. Okay? You just change, you're modifying the answer by 2%, okay? Which is acceptable for that. So this is 19.6. What's the square root of 19.6? It's going to be around 4.4 or something, 4.5. Somebody have a cell phone there?
Oh, square root? Yes, 4.4 something.
0.45?
4.427.
Thank you. So that is the velocity. Now, the steps we went through form an acronym, BizGuess, as Kaya noticed. So, which is fine. So I literally go through this process if I don't know how to solve a problem. And if I need to add a sketch, I add a sketch. If I need to add a pictorial diagram, I add a pictorial diagram. I add whatever representation I need to in order to understand this. All right? And so I will play with this and work with this. This is your strategy to set up and do problems. Okay, we have 4 minutes left. Last thing I want to ask before you get out of here. How did the homework go? There were 2 problems online. It wasn't hard. Not hard. Okay. Nathan, you'll be extended. I'll push them out till next week so you get a book and get a code, okay? There's also the introductory assignment. Did you do the introductory assignment yet, Johnson? Did you get the introductory assignment done on time? I did not extend that for you yet.
No, I got the code like the day I bought.
Okay, you did. Okay, so you got it done on time. Okay. You got your...
Yeah. I just don't understand how do you create it. Like, okay, you use the cane, like if you like take. If you use canes, you take out like a couple percent.
Yeah.
I don't know because it wasn't like that way like the first time, so I just used it for all the.
So the homework problems are all weighted. Okay, so since that set had 2 problems, it'll be worth 2 points. Okay, if the homework set has 8 problems, it's worth 8 points. It's heavier. It's a bigger assignment. It's a bigger chunk of the weight of the grade. But all the homework assignments together are worth 20 points. 20% of the grade. Okay, so you have all your summer homeworks that are homeworks. And so those, if there's 17 problems in the first one, it's worth 17 points. Right? If there's 31 problems, it's worth 31 points. And so you just, every problem is worth 1 point, and they're all worth the same. And that way, it's just easier for me to grade it, even though I know that some are harder than others. I realize that. Yeah, we'll see. Yeah, I would say I always drop 1 homework per trimester, at least 1, always, because everyone has a bad day. I mean, everyone just wakes up late, or you fall asleep studying sometimes, or you know what, you really want to go to that party and you go. Okay, and you need to have a life some days, and so everyone needs a little slack. So everyone gets at least 1 homework low grade dropped. Okay, with all the summer homework grades on there, maybe first try we'll make it 2 grades. So you can drop your lowest 2 grades. So if you blew it on a summer homework or 2, just don't blow it after this. Okay, you already used up your grace. All right, so no trouble on the homework. That's what I wanted to hear. Okay, we have 2 minutes left. Why don't we wash coffee mugs, clean up? We're done.
I have one more question.
Yeah.
So before this question, you said there's like a slope with free fall. Like,
Yeah.
what kind of stuff is that? Like, how can you like have a slope when it's free fall?
Because there's no other force other than gravity. The only force making it accelerate is gravity making it accelerate downhill. So this acceleration is the only acceleration of the problem, and that's why it's free fall.
But there's normal force.
Okay, cool.
There is a force, I agree, but the only acceleration is due to gravity. The normal force is perfectly balanced by gravity pushing into the hill. But I agree, this is still considered a free fall problem. Some people would not consider it free fall, you're right, because of the normal force. I agree. Yeah, and we haven't dealt with forces yet, so we'll yeah. The book considers this a free fall problem in the last section. Yeah, you don't like that? Okay. Hey, next time, there will be homework on mastering physics, okay, for next time. I won't see you for 6 days. And when I see you next time, we will actually we'll work with the homework if you have questions, and then we'll jump into more interesting problems of 2 dimensions and projectiles, okay? That is the goal. And again, it is my hope to give you a test on September 20th or 22nd. No, 21st. It's a Wednesday. So Wednesday, September 21st will be your next test over those units, but I emailed you that.